Hello everybody. In today's session we'll solve some problems from the polyphase circuits. In the last session I did this first problem what you are seeing on the slide. So the problem is like this: a 3-phase 230 volt supply is given to a balanced load which is delta connected. Impedance in each phase of the load is 8 plus j6. Determine the phase current and the total power consumed. In solving this problem, first we see what is the connection of the load. Now if you see the solution, the voltage what they mention in the problem for 3-phase circuits, unless otherwise mentioned, it will be line to line voltage. In a delta connected system, the line voltage and the phase voltage will be same. Therefore I mentioned here the phase voltage is equals to 230 volts. So the second line says it is a balanced delta connected load. So all the 3 phases will have equal impedance. So impedance in each phase of the load is 8 plus j6. So if I convert that into polar form, I will be getting an impedance of magnitude 10 at an angle of 36.86 degrees. And in the case of delta connection, the phase current will be phase voltage divided by impedance. So I just divided this voltage with the impedance value, I am getting this current. Now in the case of delta connection, the power will be given by root 3 times VL IL cos phi, or I can also write the power as 3 times the phase voltage into phase current and the cosine of the angle between voltage and current. So both these are all phase values, okay, voltage is phase voltage and the current is phase voltage. Therefore I just substituted the values. 3 V phase is 230 and I phase is 23 cos 36.86. Okay, so this value comes to be 12,696 watts or 12.696 kilowatts. So in all the 3-phase problems which are like this, you need to find out the phase current by dividing the phase voltage with the impedance. So for that, first we should see what is the connection for the load. Okay, if it is a delta connected, the process will slightly differ because I need to calculate the phase voltage from the given line voltage, then divide the phase voltage with the impedance value. Okay. So this is a second problem. A balanced 3-phase star connected load of 150 kilowatts takes a leading current of 100 amperes with a line voltage of 1100 volts, 50 hertz. Find the circuit constants of the load per phase. So I will just going the reverse way. Okay, here the solution, the first step will be the load power and the line current. These are all mentioned in the problem. Okay, load power is mentioned as 150 kilowatt, line current as 100 amperes, and it is also mentioned in the problem that the load is star connected. Okay, you can see 3-phase star connected. So for star connection, the phase current and line current will be equal and the phase voltage will be root 3 times, the line voltage will be root 3 times the phase voltage. So power in this case of circuit, power in this case will be root 3 VL IL cos phi, because the values what I know in the problem will be the line current and the line voltage. I selected this equation. Okay, so substituting this I can get cos phi from here. Cos phi will comes to be 0.7873. So the impedance angle will be cos inverse of this. So it is mentioned in the problem the current is leading the voltage. So current leading the voltage will happen only in the case of RC circuits. Okay, so there should be a capacitance in the circuit. That is why I took the impedance angle to be negative. So then impedance per phase will be phase voltage divided by phase current. Now you can see that 1100 the line voltage what is mentioned in the problem I am dividing by root 3 to get the phase voltage. So that divided by phase current or line current, because it is star connected, I will be getting a magnitude of 6.35 ohms and the angle will be minus 36.06 degrees here. Okay. Now this when I convert into rectangular form, I will be getting the impedance as 5 minus j 3.914. This minus sign you get because of this angle is negative here. Okay. So from there you can find out the resistance is 5 ohms. As it is negative, I should take this 3.914 as a capacitive reactance. Therefore Xc is equal to 3.914, which is equals to 1 over omega C. Therefore C is equals to 1 over omega into Xc. If I substitute omega is equal to 314, which comes from 2 pi multiplied by f, okay, 100 into pi. So that will be 314, Xc value is 3.914. So reciprocal of the product will give you 813.67 microfarads, okay. So here we have another problem, 3 identical coils each having a resistance of 10 ohms and a reactance of 10 ohms are connected in delta. I am sorry I missed these units here, okay, across 400 volt 3-phase supply. Find the line current and the reading of the 2 wattmeters connected to measure the power, okay. Now this is slightly similar to the first problem what you have done, okay, where there also we have an impedance of 8 plus j6, now I have an impedance of 10 plus j10 delta connected, okay, and the line voltage is 400 volts. I want to find out the line current, therefore I need to calculate the phase voltage here, okay. You can see here coil resistance 10 ohms, coil reactance 10 ohms, delta connection, supply voltage is 400 volts. So the impedance should be always written here 10 plus j10, okay, because this is reactance, I cannot add 20. See, if I add them just directly 10 plus 20, 10 plus 10 20, my impedance magnitude you see it is 14.14, lesser than 20. So I should calculate the magnitude of the impedance by taking these two components. So I should always write the impedance as 10 plus j10, okay. So when I convert this into polar form, I will be getting 14.14, because the real part and imaginary part are equal, the angle will be automatically 45 degrees, okay. So now the phase current I will calculate, because it is a delta connection. Unless I calculate the phase current, it is not possible for me to calculate the line current, okay. So the phase current will be phase voltage divided by impedance. As the load is delta connected, the line voltage 400 volts is equal to the phase voltage, therefore 400 divided by the impedance value will give you this much current. So the line current will have a magnitude of √3 times the phase current, therefore my current will be this much. Now to calculate the wattmeter reading, W1 what we derived in the last class as VL cos 30 minus phi, where that phi it will be the phase angle between the voltage, phase voltage and the phase current. So that is the angle of this current I should consider here, okay. Now the angle of current is 45 degrees, so W1 will be cos of 30 minus 45, I will be getting here, okay, this much, that is √3, that is W1 is VL cos of 30 minus phi. I should consider only the magnitude here, don't bother about the sign, okay. This is magnitude only, because it is a lagging power factor, I should consider only the sign here, okay. So like this. Now this equation what I get as per the phasor diagram what I have shown in the last class, okay, where the current, that circuit diagram, the phasor diagram what I have drawn is also drawn for a lagging power factor of phi, okay. Therefore I just take 30 minus phi, where phi is 45 degrees, okay. So then wattmeter reading W2 will be VL cos of 30 plus phi. Phi is again the phase angle between the voltage, phase voltage and current. So I will be getting this as the wattmeter reading. Both reads positive, okay. So I have another problem here. 3 similar choking coils. Choke coils are nothing but inductive in nature. Each coil having a resistance of 10 ohms and reactance of 10 ohms are connected in star across 440 volt 3-phase supply. Find the line current and reading of 2 wattmeter readings connected to measure the power, okay. Now the difference between the previous problem and this problem is impedance is same, but the connection, there it is delta connected, now we have a star connected one, okay. So the solution is not given, you can attempt the solution for this problem, because the method of solving the problem is same, only thing is you need to first calculate the phase voltage from this, okay, phase voltage, and while calculating the wattmeter reading you should take the line voltage, because as per the equation what you see in this we have VL. Only difference is the 400 should be replaced by 400 by √3, okay. So in the problem 5 I have 3 similar impedances are connected in delta across a 3-phase supply. The 2 wattmeters connected to measure the input power indicates 12 kilowatt. calculate the power input and power factor of the load. Okay. I like to do this problem on the board. Okay. Of course, I have provided the solution also on the PPT, but let us do it on the board. I have two wattmeter readings, W1 which is given by VL IL cos 30 minus 5. Okay. W2 will be VL IL cos 30 plus 5. I have one reading that W1 is equals to W2. Both are reading 12 kilowatt. Okay. Both are reading 12 kilowatt. So therefore, I say because W1 is equal to W2, VL IL cos 30 minus 5 is equals to VL IL cos 30 plus 5. Since it is a balanced load, voltage and currents will be same, therefore I cancel this. So what I have now, cos of 30 plus minus 5 is equals to cos of 30 plus 5. Cosine of the values will be same only when the angles are equal. So 30 minus 5 should be equal to 30 plus 5. Then I have 2 phi is equal to 0 or phi is equal to 0. That means here if I calculate the power factor will be cos phi, that is cos 0, which is equals to 1. That means it is unity power factor. Okay. So whenever the power factor is unity in the three phase circuits, when I use two wattmeters, both meters read equal. Okay. We can also do it like this. Instead of writing this way, I can simply write down the equation for the power factor. Cos phi is equals to cos of tan inverse square root of 3 W1 minus W2 divided by W1 plus W2. In this I have cos of tan inverse root 3, okay, numerator is 0 because both are equal, W1 is equal to W2. So 0 divided by 24 like this. So I have here cos tan inverse 0, so that is 0, so cos 0, this is equals to 1. Both the ways you can do it, okay, both are correct. Both the ways you can represent this, you can give the solution for this particular problem. The same solution, but of course what I have used the first method, I have given it on the slide. So in this problem, the power flowing in a three phase 3 wire balanced load is measured by 2 wattmeter method. The reading in wattmeter A is 750 watts and wattmeter B is 1500 watts. What is the power factor of the system? Okay. Now for this, again I make use of this equation, what I have written there. I make use of this equation, cos phi is equals to cos of tan inverse, okay, root 3 W1 minus W2 divided by W1 plus W2. The position of this root 3 is very important. You can't write this root 3 outside the bracket, okay. It should be always inside this circular brackets. Otherwise, it gives us a meaning that tan inverse root 3 multiplied by W1 minus W2, okay. So it should be always inside that root, fine, inside that brackets. So if I solve that by writing these values of the wattmeter readings, cos of tan inverse root 3, I will take here 750 minus, I have the other reading as 1500 divided by 750 plus 1500. you can just evaluate this expression, cos of tan inverse root 3, I have here minus 750 divided by 2250 . Okay. So, you take this product, then tan inverse of that, and then take the cosine of the angle, what you get, that will give you the power factor for the circuit. So, I am getting the power factor of as 0.9487 leading. Okay. Now, how can you get the leading also? I can just write down the circuit, and the circuit or phasor, or from the wattmeter reading itself I can tell you how to get that, whether it is leading or lagging. But here is the important is not the leading or lagging like that, it is only the magnitude of the power factor, it is sufficient. Okay. So, this is another problem what I have here. 3 similar coils, each having a resistance of 10 ohms and a reactance of 8 ohms are connected in star across 400 volt 3-phase supply. Determine the line current, total power reading on each of the wattmeters connected to measure the power. So, the solution like this, I took the coil impedance as 10 plus j8, I found that it is star connected, then the supply voltage is 400 volt 3-phase, line current will be phase voltage divided by impedance. So, 400 upon root 3, 10 plus j8, this gives us a current of 18.042 at an angle of minus 38.66 amperes. Now, the total power, if you want to calculate, make use of that equation root 3 VL IL cos phi, because it is star connected, the line current and phase current both are equal. So, therefore, I just mentioned here line current, this is also equal to phase current. So, I am just substituting those values in the expression per power. So, I get the power as 10 kilowatt. And then coming to the reading on each wattmeter, each of the 2 wattmeters, I have taken this W1 is equal to VL IL cos 30 minus 5, and W2, here I should be W2, I just have this is W1 only, this should be W2. W2 is equals to VL IL cos 30 plus 5. By substituting the values of voltage, current and the power factor angle, what you have 38.66 here, you will be getting the power as wattmeter readings as 2600, okay, 2.626 kilowatt and 7.134 kilowatt. So, like this. And again, this is also a problem. Okay, the solution of the problem I have not mentioned here. The problem is go like this: 3 similar impedances are connected in delta across a 3-phase supply. The 2 wattmeters are connected to measure the power input, indicate, okay, to measure the input power indicate 12 kilowatt and 7 kilowatt. Calculate the power input power factor of the load. Okay. So, power input is simply the addition of these two, because W1 plus W2 is the total power 19 kilowatt. Okay. And then when try to calculate the power factor, you can use the same expression, you will be getting the power factor in the circuit. Okay. So, here this ends the 3-phase circuits. Bantu. Hello everybody. Now, I thought of starting the transformers instead of completing the domestic wiring, which I will be doing at the end of my schedule. Okay. So, let me start the transformers, which is also one of the important subject, say module in your syllabus. So, the syllabus in this particular module will be like this: the principle of operation, construction of single phase transformers, which are divided as core and shell types, and then EMF equation, what are losses occurring in the transformers and how to minimize them, efficiency of a transformer and voltage regulation, and there are some simple illustrative problems on EMF equations and evaluation of efficiency of the transformers. See, this introduction tells you about what is the necessity of the transformers. Okay. Now, we have power stations which are located in the remote places. The generation of power will be AC, alternating voltage. Okay. So, that voltage generation what you have at 11 kilovolts has to be transmitted to a longer distances to reach the load centers. So, if I generate the power at 11 kilovolts and try to transmit over long distances, by the time I receive the power, the voltage at the receiving point will be much lesser than 11 kilovolts, because throughout the distance I have a transmission line, and this line consists of resistance and inductance. Because of the current flow through the transmission lines, there will be a voltage drop. So, that voltage drop, the generated voltage will take care and gives us a lesser voltage. So, it is not possible to reduce the voltage drop there, okay, because it is not possible to avoid the transmission lines for supplying the power. Therefore, what we do is, at the generating end, the generated voltage what you have 11 kilovolts, it will be stepped up, okay, to a higher voltages, and then that voltage whatever is stepped up will be transmitted to a longer distances or a long distances, and finally at the end of the at the receiving end, okay, there also there will be a transformer. You can see here the transformers are essential for power transmission over long distances. Without them, our power grid simply would not be able to scale up to meet the growing demand. Okay. The transformer allows practical wire sizes to be used in the overhead lines, and it reduces wire losses or voltage drops. Okay. So, more of the generated power makes it to the load for lower cost and at lower cost, we can say. So, this is very important. The third line what we are saying, to reduce the voltage drops and to send larger amount of the power what is generated to the consumers, okay, we need to have transformers in the transmission system. Okay. So, the electrical energy transmitted at higher voltage is received at the load end. Okay. Now, we use another transformers to step down the voltage to distribute the energy. At the distribution end, we use another transformer to feed the customers at 400 volts or 230 volts. Okay. So, at every stage in the power transmission, we are using the transformers. Without transformers, it is not possible to have a electrical power system. Okay. It is possible, but it is not possible to transmit the larger amount of powers. So, the transformer is playing a very important role in the power transmission and distribution system. Without the use of transformers, the efficiency of the transmission system will be very less. See, for example, I have a TV at my house. So, the input voltage should be around 230 volts. Think about generating a transmission, the electrical energy at 11 kilovolts and transmitting up to 11 kilovolts. Is it possible to connect the 230 volts device to 11 kilovolts? Okay. So, the device is rated to operate only at 230 volts. If I give to 11 kilovolts to that, what happens to that? And moreover, it is not possible to go up to 11 kilovolts. How? There should be larger amount of insulation. Reaching that 11 kilovolt point itself is very difficult for us. Okay. Because the voltage is quite larger there. So, therefore, I need to have a transformers. Now, at the generating end, we will have a transformer where the 11 kilovolts will be stepped up to either 33, 66, 220, 440 like that. Okay. And that power which is stepped up to a higher voltage will be transmitted to a larger distances. So, advantage of transmitting the power at larger voltages, it reduces the conductor cross section and also decreases the power loss during the transmission. At the receiving end, okay, say that is near to the cities or in the cities, we will have a substation where the power which is received at 440 volts or 220 will be stepped down to 11 kilovolts for the distribution purpose. and at every corner of the city, okay, or localities, you can find out transformers, what we call them as distribution transformers, which receive power at a 11 kilovolt distribution level, and the lines which are coming out from the distribution transformer, that is the roadside transformers what you see, they are all called feeders. The feeders will be at either 430 volts, 400 volts or 230 volts. So wherever I want a consumer to have a 3-phase supply, I can connect him to the 430 volt system. Otherwise, if I have a single house where I don't need the three-phase power supply, I can connect that particular house across one phase and a neutral, giving us a reduced voltage of around 230 volts. So that is called a single phase load and a 3-phase load. So this 3-phase and single phase loads can be connected to the distribution transformers. Without distribution transformers, it is not possible to supply the residential consumers. There are bulk consumers where they receive the power at 11 kilovolts directly from the substation. Okay. So this is what the necessity of the transformer. Now what is a transformer here? So electrical power transformer is a static device. Okay. Static in the sense there are no rotating parts, both the parts are stationary, which transform electrical energy from one circuit to another without any direct electrical connection and with the help of mutual induction between the two coils or two windings. It transforms power from one circuit to another without changing its frequency, but maybe in different voltage levels. So this is what the function of a transformer. Okay. So coming to the working principle of a transformer, the working principle is like this. It depends on Faraday's laws of magnetic induction. Okay. It actually depends on mutual induction between two or more windings. Generally, we will consider two windings for single phase transformers. Okay. Okay, two windings, and is responsible for transformation action in an electrical transformer. This mutual induction, it is responsible for transforming the electrical energy at one voltage level to another voltage level. Now there is no electrical contact between the two windings. Okay, the connection what you have is only through the electromagnetic flux. So the basic concept we can understand from this diagram here. Okay, whenever we apply alternating current to an electrical coil, there will be an alternating flux surrounded by that coil. So here any current carrying conductor will produce a magnetic field. Based on that, we have this line. I have a coil, I am connecting a supply to the coil, therefore this supply will allow a current to flow to the coil. So that current will make the coil to produce a magnetic field. Now all currents will produce a magnetic field definitely. When I connect an alternating source, the flux produced also will alternate. Okay. Therefore, if the source follows a sine curve, the magnetic flux also follows a sine curve. If I bring another coil near the first one, there will be an alternating flux linkages with the second coil. What all the flux produced by the first coil will be linking with the second coil. How much amount of flux links with the second coil, that depends on the proximity of the second coil with respect to the first one. Okay. The closer the coil, more flux will be linking to that. Now as the flux produced is alternating, the flux linkage also alternates. Therefore there will be a rate of change of flux linkages in the second coil with respect to the first coil. Okay. Now as the time changes, the flux linkage also changes because the flux is sinusoidal. Therefore there will be a voltage induced in the second coil as per the Faraday's laws of magnetic induction. Now so this is the basic principle of a transformer. Now the winding which takes electrical power from the source, that is called as a primary winding. The first coil is called as primary. The winding in which there will be a desired output, okay, that is the induced coil due to the change in the flux linkages, that is called as second coil or secondary. Okay. Now this secondary coil which has an induced EMF in it due to change in the flux linkages, okay, will give us a current when it is closed. When the second winding is connected to some load, there will be a current flowing through that. Otherwise, if I connect a voltmeter across the second coil, it gives us the amount of voltage induced in the second coil. Okay. So the winding which gives the desired output voltage due to mutual induction in the transformer is known as the secondary winding. Generally, the winding which is connected to supply, that is called as primary, and the winding which is connected to load, that is called as a secondary winding in the case of a transformer. Now here, if I see between these two coils, there is no electrical connection. The link what you have is only the magnetic flux. Okay. Now the flux lines are just moving through the air and linking with the second coil. Fine. Now this, instead of allowing the flux linkages through air, if I provide some medium, okay, some medium between these two coils, so that medium can carry a flux, I will get more amount of flux linkages in the coil, second coil. Okay. That is what I am telling here. In open air, very tiny portion of the flux of the first winding links with the second coil. Okay. The current that flows through the closed circuit of the second coil will be so small in amount that it will be difficult to measure, and moreover, because the current is smaller, the power what you have is also smaller there. So the rate of change of flux linkages depends on the amount of linked flux. So by making more amount of flux linkages, I can have more amount of voltage induced in the second coil. Okay. We always aim to do that, that is, we will like to have most of the flux produced by the primary winding link with the secondary winding to have larger amount of power transfer from one circuit to the other circuit. So this can be increased by placing a path. What should be that path? That path should have low amount of reluctance. Okay. Now generally in electrical circuit, when the resistance is smaller, I will be getting more current. Similarly in magnetic circuits, whenever you have a low reluctance, that path will carry larger amount of flux. Okay. So the low reluctance path is the magnetic core of the transformer. Okay. So through which maximum number of flux produced by the primary will pass, because it is opposing, its opposition is less as the reluctance is less. Therefore, most of the flux produced by the primary winding what you have will move through this core and links with the secondary coil. Therefore, I will be getting larger amount of voltage here. That voltage will give you a measurable current in the output or to the load. So a transformer basically now will have three parts: primary winding, which will be connected to supply, secondary winding which is connected to the load. In between these two, I have a magnetic core. So if we see the construction of the transformer, these are the three main parts what I told you. The primary winding of a transformer, which produces the magnetic flux when it is connected to electrical source. Then we have a magnetic core of the transformer. The magnetic flux produced by the primary winding pass through the low reluctance path, links with the secondary winding and create a closed magnetic circuit there. Okay. So this secondary winding of a transformer, it will be having the flux linkages produced by the primary, okay, and they will be changing the flux linkages because the flux is sinusoidally varying, right. Now this core is all, this flux is also wound on the same core. So therefore I will be getting a voltage induced in the secondary winding because of the Faraday's laws of magnetic induction. Now if I see the core of the transformer core is constructed by assembling laminated sheet steel. Okay, we stack them together, laminated sheets of steel with minimum air gap between them to achieve continuous magnetic path. Okay, if there is any gap here, air gap, the air gap will have a larger amount of reluctance. Okay, it offers larger amount of reluctance, so it will allow a low amount of flux produced in the core. So therefore we need to avoid the air gaps there. Okay. the steel used is having high silicon content and sometimes heat treated to provide high permeability. High permeability means reciprocal of that will be reluctance. Okay. So, when you have a higher permeability, more ability to conduct the flux lines, okay, and low hysteresis loss. This is very important. Any magnetic material, when you subject the core to a reversal of magnetism, it gives us a curve called BH curve. The area under the BH curve will tell about how much amount of energy wasted during the flux reversals. If you have a material for the core which has a wider hysteresis loop, then the amount of energy wasted during the flux flow through the core will be larger. Okay. I cannot use that energy anyway, so it just produces heat in the core. So, that energy losses what we are getting in the core because of the flux reversals, we call it as hysteresis loss. Flux reversals in the core is required for me, otherwise there won't be any induction of voltage in the secondary. So, if I want to transfer electrical power from one voltage level to the other voltage level, the reversal of flux in the core is compulsory. Without that I cannot do the transfer of energy from primary to secondary. Okay. So, therefore, I need to provide a magnetic core which allow more amount of flux through the core, at the same time produces lesser amount of hysteresis loss. Okay. The laminated sheet steels of steel are used to reduce eddy current losses. What is this eddy current losses means? See, the material what I am using for the core, it is steel, okay, or alloys of steel. So, it is also a conducting material. Any conducting material, when it is subjected to reversals of magnetism, there will be a induced voltage in them. So, now the magnetic core also will have a voltage induced in it. So, the induced voltage will have set up a current in the core also. So, this current depends upon the cross sectional area or the resistance offered by the core to the induced voltage. Now, if I use a solid core, the area will be larger. So, the resistance is smaller. So, therefore, the induced voltage in the core will give you large value of current. I cannot take out the current, use it for other purpose, because I have no access to the magnetic core. I have access only to the primary terminal to connect a supply, secondary terminals to connect a load. So, since it is not possible for me to take the induced current in the laminated in the core, so it is just produces a heat. So, to minimize that induced current, I need to increase the resistance. To increase the resistance, I need to reduce the cross sectional area offered by the core to the induced voltage in the core. So, therefore, to reduce that area, instead of using a solid core, I will be using laminated sheet steels. Now, these laminations are insulated from each other. So, because of the insulation, whatever the voltage is induced in the lamination, it is confined only to the lamination. So, the current induced by this voltage will also confine to the lamination. Because of the insulation present between the two laminations, the induced current in the lamination will restricted only to the lamination, therefore, it cannot go to the next lamination. So, because of this, the area offered by the lamination to the induced voltage decreases, so that increases the resistance. So, therefore, the induced current magnitude in the lamination also decreases. It is not possible to avoid this induced currents, because core will always carry the flux in the two directions, or the flux keep on alternating sinusoidally. Therefore, there will be an induced voltage in the core and there will be an induced current. So, this induced current, because it is minimized, the loss what I am having is also minimum. So, to avoid high reluctance at the joints, laminations are stacked by alternating the sides of the joint. So here I have shown, I am using different types of laminations here, E-shaped laminations, I-shaped laminations, L-shaped. So when I am using E and I together, I will get a core like this. And when I use L-shaped lamination, you can see one lamination is L-shaped like this, the other one will be like this, okay. They are arranged here. Now there is a joint here, you can see, okay. This is a joint. So to avoid the air gap, then what I do is, the next lamination what I get here, it will be in the reverse way, okay. That you can see here, okay. This is E-shaped lamination, then I have a I-shaped lamination. So there is a gap here between the E-shaped lamination and I-shaped lamination, there is a gap. To avoid the gap, you see how the next lamination is arranged, okay. That E portion is coming down and I portion is coming on the top. So therefore, what you have a gap here and the gap here, this gap is covered by E-shaped lamination and this gap what you have is covered by this lamination. Like this, we have laminations arranged in this fashion to give us a core. If I see the core here, it appears to be solid in cross section, but actually it is not solid, because the laminations what we have here, they are all insulation coated, okay. There will be a varnish coating on both the sides of the laminations and they are stacked together. Because there is a lot of procedure will go into the manufacture of these laminations, but for our purpose it is just sufficient to know that the core of the transformer is laminated with an insulation between the laminations. Now the insulation what you have between the lamination, it cannot carry any flux, okay. So the flux will not be flowing to the insulation between the lamination. So I have the types of transformers based on the construction of the, can be classified on different basis, like types of construction, types of cooling, etc. So on the basis of construction, I have a core type transformer or a shell type transformer. On the basis of their purpose, I can call the transformer as a step up transformer or step down transformer. And on the basis of type of supply, it can be a single phase transformer or 3-phase transformers. Single phase transformers will be connected to single phase supply, 3-phase transformers can be connected to 3-phase supply. It is also possible to use 3 single phase transformers connected together for a 3-phase operation. It is not required for our syllabus. So let us now just consider only single phase transformer which is there in syllabus. So we study only the operation of single phase transformers, okay. On the basis of their use, I call the transformer as power transformer, distribution transformer, instrument transformers and all. Instrument transformer, there are 2 types. I have a current transformer and a potential transformer. Current transformers are just used for the measurement of current, and the potential transformers are just used for the measurement of voltage, okay. As it says, instrument transformers, it is the purpose of using this transformer is only for measuring, okay. They won't supply any larger loads, right. Always these are all step down transformers, okay. Instrument transformers are always step down. If they are stepping down the current, I call it as a current transformer. If it is stepping down the voltage, I call it as a voltage transformer or a potential transformer, okay. On the basis of cooling employed in the transformers, I call it as oil filled self cool type, oil filled water cool type, okay, and air blast type. All these transformers what you have, power transformer, distribution transformers, these are all can be generally 3-phase transformers, okay, and single phase transformers are also used, but to a say their application is limited. In the power systems normally we go for 3-phase transformers. All these transformers can be step up or step down transformers, okay, and they can be core type or shell type also. So the basics, actually basic construction, it is core type and transformers and shell type transformers. We concentrate only on this construction, okay, classification based on construction we concentrate. So in a core type transformer, the windings are cylindrical, former wound, okay, mounted on the core limbs, right. Of course I just said here shown in the above figure, the figure is not there here, I will be showing the figure in later. The cylindrical coils have different layers, each layer is insulated from each other Materials like paper, cloth or mica can be used for insulation. Generally mica or paper will be used. Low voltage windings are placed near to the core as they are easier to insulate. Okay. I will show the diagrams later. The coils are former wound in the shell type transformer and mounted in layers stacked with insulation between them. A shell type transformer may have simple rectangular form or it may have a distributed form. Okay. So this is what we have, a core type transformer. These are our laminations, core here, these are the coils. You can see before placing the coil there will be a insulation and there will be a winding, then again there is an insulation, there will be a winding. So as I have just given mention here, first I will be placing the low voltage winding. LV insulation will be there. Before placing the winding there will be a insulation between the core and the LV winding. That is what I call as LV insulation. Then I have a LV winding. Okay, the white color what you see here is insulation, blue color is the winding. Then again there will be a insulation between LV and HV, which we call it as HV insulation. Then the outer surface what you are seeing here will be the HV winding. Okay. Now generally the core type transformers will use cylindrical windings like this. Okay, cylindrical in shape, windings will be cylindrical in shape. Always the low voltage winding will be placed near to the core because it requires lesser amount of insulation. Whereas in the shell type transformer you can see more amount of core material is coming here. Okay, therefore this iron circuit will be more, and the windings they are always placed on the center leg. I can arrange the windings in different fashions. I can arrange them concentric cylinders, like say what you have shown here. LV winding is the inside one, outer one is HV. So because the axis of these two coils are coinciding, I call them as concentric winding arrangement. I can also have like this. Okay, or I can also have a sandwich arrangement, that is the winding will be divided into a number of sections. Then I will arrange first a low voltage winding near to the core, then a high voltage winding, then again a low voltage winding, then a high voltage winding, like that. There are different types of arrangement for the shell type transformer. Different in the sense there are only two types actually. One is called cylindrical arrangement like this, other one is sandwich type. Okay. So this is another arrangement for the windings on the transformer. You can see I have a core, magnetic core, then the inner one is LV, this is LV, and this is outer one is HV winding. Okay. So I have the core is uniform in cross section. Here the core has 3 legs, but it has only 2 legs here. The core, the flux, if you see, the flux is uniform in the core transformer. Every portion of the core will carry the same amount of flux phi, whereas here the core, the center leg what you have, limb, okay, I call this as a limb or leg. 1, 2, 3 limbs are there. The center limb will carry larger flux compared to the outer legs. So these are the two arrangements. One shows the core type transformer, the other one shows the shell type transformers. The construction is only difference, but operation wise there won't be any difference in the transformers. So I have a slide here to show a comparison between the core and shell type transformers. So the core has only one magnetic circuit, that means the core cross section is uniform. There are 2 paths for the flux in the core. The cross section of the center leg will be normally double that of the outer legs or outer limbs. Core has 2 limbs. Here now the core has 3 limbs, center limb, 2 outer limbs. There may be a difference in the cross section, but the number will be 3 here. Okay. Magnetic flux is uniform at all sections of the core. Here the central limb carry double the flux compared to the outer limbs. Coils are placed on 2 limbs. There, here in the shell type I am placing the coils on the center limb only. Now winding surrounds the considerable part of the core. This is with respect to the previous diagram. You see here we have only the outer portion, the upper portion of the core and the bottom portion of the core, what we call them as upper yoke and the bottom yoke. These two are only exposed to the outside air. Okay, if I just consider only the core, only the transformer. okay, not the enclosure and all. Here you can see the outer legs are exposed to more air, okay, atmosphere more. Like this, if I come to this next slide, I have two more comparisons, points to compare. Natural cooling is provided in the core type transformer. Difficult to provide natural cooling because cooling medium has lesser amount of access to the windings, whereas here core type I have more access. And then easy access to the winding make maintenance easier. Mechanical protection to the coil is lesser in the case of core type transformers, whereas these two parts will be more, okay. Less access to the winding makes maintenance difficult in the case of shell type transformer. Core protects the winding in the case of shell type, whereas the core protection to the windings is lesser in the case of core type transformers. I will be ending my session here. In the next session, that is tomorrow's session, we will see what will be the EMF equation for the transformer and what are the losses, okay, and how to minimize these losses also. We will see that. Thank you.